We have next two speakers from Nuclear Fuel Complex, Mr. Jeetendra and Mr. R.S. Kulkarni. Jeetendra Bavrani, Maintenance Engineer, Department of Atomic Energy, Nuclear Fuel Complex, Hyderabad, joined this Department of Atomic Energy in September 2002 as Trainee Scientific Officer and underwent 1-year orientation program at BARC training. Mr. R.S. Kulkarni, DGM Maintenance, Tube Smelting and Q&A, Department of Atomic Energy, Nuclear Fuel Complex. I would like to invite both of them on the stage.
Good afternoon. At the outset, I would like to thank Mr. Raman sir for giving an opportunity to share our experience with whatever we do at our shop floor. Nuclear fuel complex, I'll cover a little later. So we have basic responsibilities. Of course, we have now a greenfield project coming up at Rajasthan, Kota, and the complex which is at Hyderabad is basically a brownfield. We have lot many systems with a different complexities. So one of the case studies which we have chosen is to upgrade one of our die making machine. So before getting into the actual job, I want to just brief about our organization. Probably you must be knowing Nuclear Fuel Complex is one of the important unit of Department of Atomic Energy, and it is responsible for the manufacturing of all fuel bundles for nuclear reactors which are running and also which are being planned in the future. This particular topic, of course, is development of electronic cam-based technology of manufacturing a rolling mill die against conventional hardware template based on the systems. Why we have chosen this particular one is it is in line with what the theme of this particular forum, navigating the new age of innovation. Even though it is, see, one of our challenges, whatever machine is and whatever its age is, we need to maintain, and especially nuclear fuel complex, many systems which are about 20 years, 25 years, we are able to maintain and get the product. So that is the reason I have chosen this. So our basic responsibility is to manufacture the bundle, that's fuel bundle. And this manufacturing is right from ore to the core. All processes are being done in one roof. So the down below are the photographs of various plants of NFC. And the fuel bundle manufactured at Hyderabad has been catering to all nuclear power plants scattered all over the India. So these are all the indications that various nuclear power plants located in different parts of the country. So every month we need to ship the nuclear bundles. Each reactor needs about 200 bundles on a monthly basis. There are two products in this. One is fuel from the uranium ore. We'll have to extract the fuel and we have to make it into a pellet form, and we have to manufacture the tube in which these fuels are loaded. So we have a line for tube manufacturing, we have a line for the fuel pellet manufacturing. And based on our present requirements, because after 1, 2, 3, the new material is coming up. Now we have to gear up for all the requirement for the future reactors. For that, see, a new NFC is coming up at Kota with a rated capacity of 500 tons per year to cater to the fuel requirements of Kakrapara, 700 megawatt unit, and also for Rajasthan's. These are all a few photographs. I was talking about that pellet. this is the pellet in the final form. So we start with the ore from magnesium diurenate, and we have the various process like solvent extraction, precipitation, sintering, reduction, and then not sintering actually, it is a calcination, reduction, and then final compaction and sintering. Then after sintering, we'll get these pellets, and these pellets will be loaded into this bundle. So there is another plant which does this assembling of this. The tube side plants, we manufacture different sizes of tubes. You can see the entire different dimensions in this. And this is the fuel bundle for Tarapor's reactor, which was initially started in 1969 in collaboration with Canada. And it is still, we are supplying these fuel assemblies. And this is the new fuel assemblies for PFBR 500, which is coming up at Kalpakam. Yeah, of course, this is from the process point of view. But once you come to instrumentation and control, it remains same, irrespective of the industries. We need to say the same challenges as other industries. So challenges are, we have old systems, we have all process parameters, we have a different kind of control systems, PLCs, DCS, SCADAs. We need to maintain them irrespective of whether a manufacturer supports or not. The requirement is high availability of equipments. So as I explained, it is older machines, lifecycle management, obsolete technology, no space supports in many cases, retrofitting. Only when this is there, we need to sort for retrofitting. And the case study which now Jeetendra is presenting comes under this category. New machines with the latest INC components with the present day technologies. Then that we need to have proper training with different exposures. Then I say this is one of our strengths. We have a very well-trained manpower, both at technicians, supervisors, and engineers. Many of the systems which suppliers have not supported, we could explore and then maintain the equipment to get the high availabilities. One of the examples was our extrusion press, which was installed about 30 years back. Now, even today, it is performing at its best. Of course, with the latest INC package, which is being done by our engineers. I leave this to Jeetendra to explain this particular case study.
Ladies and gentlemen, very good afternoon to you. I thank you, sir, for giving me this chance to explain about this case study. Here, my colleague Mr. Kulkarni just explained that we put pellets into the tubes and make a bundle which subsequently goes into a reactor. So, for making these tubes, and there are so many of them, as on today's production rate, we manufacture about 200 quality assured tubes. 200,000. It's 2 lakhs per month we are manufacturing the tubes. To manufacture the tubes, we use a lot of process steps which involve like melting, followed by extrusion, and finally, since the tubes are to be seamless, we follow rolling process to make them. Now here, just to appreciate the process, I would request you to just ponder over these two words like ring dice and tapered mineral. While keeping these two words in mind, I would request Raj to please play the video first, wherein we can just appreciate what a rolling process is. Yeah. So this is a generic rolling process. Here you can see any blank which is input to the rolling press is gradually reduced in the dimensions. The wall thickness is reduced and overall diameter is also reduced. You can see like this is the ingoing portion and this is the outgoing. So the tube cross section is getting reduced. Now here important thing is I told you to remember regarding ring dies. So this ring dies will have a profile kind of thing. You can see here the depth is high, here it is low. So as the tube is passed through these rolling dies, the cross section reduction takes place. You can switch it off. Yeah, here. So here it is depicted the very process which have we seen in the video. Now, how to make these dies? Or if you see here the below picture, the profile will change from lower depth progressively to higher depth, and this profile changes very smoothly from 0 degree to 360 degree. Okay, so it means if I talk at any particular point on the periphery of the die, the profile will be unique, the depth of the cut will be unique. So as I said, the number of production, the tubes which we produce is very high. So to produce the tube, we should supply these dies also. So we have a profile cutting machine in which this job is executed. So this design data, now what are the design parameters possible here? See, what is the reduction we want in the tube, in the diameter, and second is the wall thickness. So based on these two parameters, we enter into this machine and this machine is run, which gives us these dies. So I have another video to explain about the functioning of this machine. It will help us to better appreciate the process. You can see these two are the dies. In between there is a tool which is cutting simultaneously on both the dies. Now these dies are rotated gradually on their axis. At the same time we increase the eccentricity in the tool, which gives us the required depth of cut. Fine. Now how the machine is able to give this? The dies which are to be produced are mounted on these two beds, left die and right die respectively, on the left bed and right bed, whereas the tool is in between, which is provided the eccentricity. Now the whole issue here is to control the eccentricity based on the profile requirement. Suppose I am at 180.00 degrees. So at that point of time, what is my depth of cut required? That profile somebody should feed. Now how it is fed in the conventional system, this you can see run both the dies in synchronism first of all, because I should have both dies having the same depth of cut at every point across its periphery. Then eccentricity is introduced and then simultaneous cut is achieved. Here is how the conventional method we used to have to produce these dies. Whatever profile of cut is required from 0 degree to 360 degree is translated into one metallic template like this. Alright. So this metallic template is machined, it is made by hand, and it will have at any point of time the required depth of cut parameter. In the next step, this template is installed in the machine. Now how this template is able to give the system that at any point of time I need this much depth of cut. So for this purpose, the template is traveled in synchronism with the die rotation, so that at any point of die, what is the depth required is generated by this template. This template will push another sensor which will generate the pulses, based on the push or pull. This is a spring-loaded sensor. If you see if I travel like this, it will push the sensor, which in turn will generate the pulses. These pulses will be fed into one position control loop, which will also have the actual position feedback from the motor encoder, and it will control the servo drive to position this axis at the required set point. I hope I am clear till now. You can also interrupt me wherever you want, within my time of course 30 minutes. So this was the old process. This was a 35 years old control system which we were maintaining. Now we wanted something innovative to achieve the same task. Of course, it's a very old technology what we used to have. So then we went to something called a motion controller based system, in which whatever template profile you want, there is a tool something which is called Cam Builder. So in that you enter the profile from 0 to 360 degree. Okay, and here there is no restriction on the number of points. You can use up to 1000 points to define your trajectory of the eccentricity. Then you download this profile into the motion controller, and then motion controller will run a virtual master in it, see, which is analogous to the physical metallic template running. All right. Now this motion controller will generate the trajectory, and which he will be feeding to individual axes. So we have seen in the previous that there were 5 axes in the system. Each axis must be positioned based on the profile. Now this motion controller, it's a new architecture of new system. It will send on this Ethernet based interface in real time. It will transfer the position set points to servo drives, and servo drives will position the respective axis. So this becomes my new HMI through which I can feed my template into the motion controller, download it and start working. So all synced, system in operation. This is just a block diagram of how the system is working. As I explained earlier, the virtual master will run here, and which will also act as a master, and master's actual values will be given to the 2 dies rotating, to left and right beds where it has to be kept dynamically, and then eccentricity, how much has to be introduced at any point of time. So this is just a comparison of between old and new system. Here I am developing old, in the old system, if you see, I must prepare this metallic template which will run and press this sensor. These are the sensor generating profile set point, and this is a metallic template. Here I simply design an Excel file, or I can design the Cam Builder software and download into the motion controller. So just in one slide I would like to bring the major tangible benefits which are offered by the new system. No hardware template linear sensor combo. See, making the hardware template is a manual process. When we make these dies, we talk the accuracies of the level of few microns, 2 micrometers, 3 micrometers, 5 micrometers. So if I make the template and run with the help of sensor, the sensor will have its own inaccuracies, hysteresis, and there will be some limitation to the accuracy with which we can manufacture the template also. So in the new system there is nothing like this. Whereas at any point of time, let us say I want a 3.2550 mm depth of cut. The same in digital format will be conveyed based on Ethernet to the respective control drives. So there is no inaccuracy in generation the profile. Second point is smoother profile. In the older system, it's a metallic template. I cannot have infinite number of points. The points have to be fixed. It used to be 51. Now I can have 1000 points, which gives me very, very smooth profile, which in turn obviously will have an implication on the quality of the tubes also, because ultimately these dies are going to make the tubes, right? Faster design to delivery time. Earlier, the designer will give an Excel sheet to the operator, he will make the template, he will mount it, he will run, he will try. Now nothing, just give Excel file, download, start working. So my design to delivery time has come drastically down. Similarly, electronic compensation of mechanical errors. The system which are based on ball screws, it's a servo axis, will have some errors like backlash and all that. So I can compensate, I can measure those errors first, then I can compensate in machine data of every axis, which will give me further better accuracies. Energy saving, of course, due to elimination of one complete axis. Earlier when I produce a die, it will have 6 axes. Now when I produce a die, it will have only 5 axes. So it's a tangible benefit in terms of energy saving. And very informative and convenient operator interface. Maintenance free AC servo motors. Mind you, the DC motors which were there earlier, they were all carbon brush DC motors wherein you have to maintain them regularly. Otherwise it will form a carbon and it will even push the system into oscillation. We have observed many occasions that it starts oscillating any particular axis and clean the brush and remount and it starts working again. So no such problems now. Easier troubleshooting with the aid of advanced technology. I will just share with you some pictures of old servo drives and the control system. You see, this is the TTL based control system what used to be there earlier. Now here just imagine if just few wires are cut even by some rodent entry, we'll spend maybe a few months to diagnose where is the problem. And this is a comparison of this just old operator desk with very few information. The new one is dedicated screens for the maintenance engineers wherein they can simply find out where is the problem. So I have 2 minutes left, which I will use to thank maybe Ganpati sir to give us the opportunity. We just submitted our presentation very late. So thank you one and all. Thanks for the patient hearing.